Good morning, ladies and gentlemen. We are going to proceed with the continuation of the session morning, and it involves two honors lectures. The first one is the honor lecture of the Technical Committee TC 101, and the lecture is going to be introduced by the TC Chair, Erdin Ibrahim, from the University of Bristol.
Good morning. Thank you very much for attending this lecture. TC 101 on laboratory stress strain testing of geomaterials established Bishop Lecture in 2009 in commemoration to late Professor Alan Bishop, to be delivered by the world's most distinguished figures in experimental soil mechanics. Professor Alan Bishop was one of the pioneers of advanced geotechnical laboratory testing. His original designs for scientific apparatus, meticulous attention to experimental detail, and rigorous approach to interpretation were acknowledged internationally. He was also highly successful in applying his research into geotechnical practice, particularly in the field of embankment dam engineering and slope stability assessment.
Thank you. It's now my pleasure to introduce the Bishop Lecturer, who is Professor David Muir-Wood. Professor David Muir-Wood got a BA in Mechanical Science from the Cambridge University and also a PhD from the same university on some aspects of the mechanical behavior of kaolin under truly triaxial conditions of stress and strain. The PhD was supervised by Peter Roth. He has many distinctions. I'm just going to mention two. He's a Fellow of the Royal Academy of Engineering in the UK and the Fellow of the Royal Society of Edinburgh. And he's currently at the University of Dundee, UK. Actually, I'm going to finish with a personal note. Professor Muir-Wood was actually the examiner of my PhD thesis long, long ago. And I can confess now that I was somewhat concerned that my examiner was somebody who knew everything on soil mechanics. Please, David Muir-Wood, take the rostrum.
So the first thing I should do is to thank the Technical Committee 101 for inviting me to give this lecture. And we should express our sympathy with Professor Koseki, whose mother is ill at the moment and not able to be here. He's not able to be here. So I'll talk about, well actually, let me start off by the prologue. Back in 1973, Peter Roth and Andrew Palmer organized a meeting at Cambridge University on the role of plasticity in soil mechanics. And this photograph was taken of those present at that meeting. In the front row, you can see Alan Bishop himself, AWB. And in the back row, looking rather young, you can see your fourth rank Bishop Lecturer here. I was a very young research student at that time. There are some other people here were also present on that occasion. Could you like to put your hands up if you can see yourself in the photograph? There are probably half a dozen who are here, but it's an amazing picture of the luminaries of the soil mechanics world of that period in 1970s. As been mentioned, I was supervised by Peter Roth, who is in the front row there, and my thesis was examined by John Burland and by Andrew Palmer, who's there. But there are some really well-known faces there and less well-known faces there from the field of plasticity and soil mechanics. So what I want to do, that was the prologue. What I want to do is to talk about this interface between modeling and testing and to define what I mean by those things. And the three themes I'll pick out are element or system, deficiencies of samples or tests, and deficiencies of models, and then present some conclusions. The printed version of this paper has various other examples in it which I haven't got time to include in this oral presentation. So the first thing then is to look at modeling and testing. As has been mentioned, I did my PhD using the true triaxial apparatus to look at the mechanical behavior of kaolin. And since that time, I've delved into experimental work, but also into development of constitutive models. So I've been very much working at the interface between modeling and testing for much of my research career. So my definitions that I'm going to use here are these ones. That modeling is the development of models, mostly constitutive models, with which to simulate response of soil observed in more or less carefully chosen tests. Whereas testing is then the sort of converse of this, the observation of response of small samples of soil to histories of stress and strain. And we'll find that it's actually harder than we think, perhaps, to interpret these two approaches. So the constitutive model is something which mostly we don't try to spend the time dealing with. We just use it because it's the building block in the numerical analysis between the equilibrium statements, changes in stress, and the compatibility statements, the changes in strain. But it's there. And you may have to choose to use an elastic model, a Moore-Coulomb model, or a Cam-Clay model. These are all familiar names of models that we'd use in numerical analysis. But all testing that you perform is conducted in the context of a particular model, either willingly or unwillingly, consciously or unconsciously. For example, much testing is done in order to choose parameters for a model itself. That's a common theme. Fitting models to observations, another common theme. Rarely attempting to refute the constitutive conjectures, the way in which the models are built. But we'll see that's actually rather key. So I'm going to concern myself with continuum models, which is to say we're going to deal with macroscopic concepts such as stress and strain, although we'll see they're difficult to define, simply because the models which I've used mostly are, in fact, described in terms of stresses and strains. So elastic plastic modeling is my theme, or has been my personal theme, but the comments that I make about modeling are relevant also to other constitutive frameworks. As I said, the printed version contains additional case histories for which there's not space in this lecture. So the first thing is then element or system, and thinking about intermediate scales. What is the size of the representative elementary volume that we might define for a real soil material? And the question really to associate with that is this one. How large should a sample be in order that it might appear homogeneous? The first guess would be to say that the scale of the problem is set by the median particle size D50. But it will turn out that's really very optimistic as a guide. But this idea of the particle size influence is relevant because when we start thinking about a scale, then that rather indicates the sort of size of sample that we need to fit in the number of cells of behavior. We'll see that in a moment. So the first thing is then to look inside the sample. And we can look inside the sample, first of all, in terms of deformations. That seems to be the easier thing to do. And I'll pick an example, an elaborate apparatus, but one in which we can see quite a lot about the behavior of the material. This is the so-called 1-gamma 2-epsilon apparatus developed at Grenoble. When I first saw this apparatus, it was made out of Technic Lego, but it's now made out of rather more substantial materials. But it's a plain stress apparatus in which there's no movement in the, or nothing happening in the out of plane direction. And it's a plain stress apparatus which uses an analog granular material, not real soil, but actually rods, a so-called Schneebeli material we'll see in a moment. It's a directional shear cell in which all the plane strain components can be applied. You can have one shear strain, and you see the shape of the sample changing here, and also apply direct strains in the horizontal and vertical directions. So there are these two direct strains and one shear strain. Here is the grading of the material tested. It's an analog material with three sizes of rods, 1.5, 3, and 3.5 millimeters in this case. And this is a typical result from fairly early on in a shear test on this material. We start off with essentially a uniform distribution of these rods, but very quickly, in the very early strain stages, you see that the shear strains and the volumetric strains show really quite a structure of variation, and you certainly couldn't say that they are varying uniformly across the sample. So there's clearly something happening which is to do with not just the particle size, but to do with a scale bigger than the particle size. So we've got homogeneous boundary displacements, but the internal strains are clearly showing something which is quite clearly patterned and heterogeneous. And I think that when one looks at these things, one sees that the stage at which these strain features develop is very early on, and it's almost as though the heterogeneous state is the natural state of these soils. In this case, we can sort of look and see perhaps there's a cell size with a dimension of the order of 15 times d50, perhaps up there. So that would be an indication of the sort of size of a block, building block, from which you might build up observations. Here's another case, using X-rays to identify the density changes occurring in soils when they're being sheared. And these are X-rays associated with a rotating wall, so it's rotated from the vertical to this inclined position here. And as it does so, it sort of squeezes and shears the sand behind and in front of the wall. And you get these patterns of dilation bands, giving you something like a cell size of perhaps in the order of 30 times d50. You may need to have the eye of faith to see these things, but these patterns that I've drawn here do sort of come out of this picture at the top. Well then, if that is the size of the cell for which you reckon that there's a sort of pattern occurring, how many cells do you need to define a representative element of this material? 10? A bit small. 50? Perhaps. 100? Better, perhaps. But it means that then the size of this sample should be, as it might be, 50 or 100 times the size of this cell, which is quite big by comparison with the particle size. So our decisions previously made on the basis of particle size now have to be revised in terms of this cell size, which is much bigger than particle size. That's looking at look inside the sample using strains. Can we say anything about the stresses? Well, we know that Berlin said that stress is a philosophical concept. We cannot see stresses, we can only see the consequences of stresses. But if you have a birefringent material, as we'll see in a moment, and we can use analog soil particles and see them, visualize them under polarized light, and then see patterns which give us some indication about the stresses within those samples of the material. So, for example, you have a disk which has been being subjected to diametral load of progressively increasing magnitude. You find that you get as you observe this under monochrome polarized light, you get a series of fringes forming, and the pattern of fringes progressively develops as the load increases. So that as you go from low load to high load, so the number of fringes increases. Low load here to much higher load there. And this pattern can be used to deduce the stress difference in principal stresses within the particle, the material under study. These are diametral loaded particles. And just by the way, if you have a spherical particle, you can also see these same sorts of fringes within that particle. And here's a bit of crushed glass as well. The same thing applies for that. But of course, it's much harder to interpret these things when you have a rather irregular shaped grain as opposed to the single disk of the previous case. But these are the tests done by Drescher with Jocelyn de Jong back in the 70s, classic tests showing the effect of having stress changes on an assembly of photoelastic disks. And the right-hand diagram, well, the main diagram shows the disks themselves. The lower diagram shows the interpretation of a picture like that in terms of the forces between the particles of the photoelastic picture. So the thickness of the lines indicates the size of the interparticle force. What you clearly see from this immediately is that there's a huge variety, huge variation in the way in which the stresses are being transmitted through this particle assembly. So looking at the picture looking at the main picture, some particles have no stress in them at all. Some particles have very heavy stresses in them. And this is something which has been found also in discrete element modeling. And in a sense, the DEM work has done nothing but show that the photoelastic pictures of Drescher and Jocelyn de Jong were correct in terms of the modeling that has been done with the DEM more recently. We see columns of particles carrying the load. We see that the adjacent particles may carry very little stress, but actually are there to provide a bit of resistance against the buckling of the main columns. And you can imagine that this whole assembly is very sensitive to rotation of the principal axes. So you just look at these various cases ringed here. Some of them indicate very high stresses at the particle contact. Against the unloaded boundaries, then there's very low stress. Obviously, there's zero stress in the voids, and some particles themselves have no stress in them whatsoever. So the concept of stress in a particular material obviously is something which is really quite difficult to get to terms with. Well, okay, let's see how small an element can appear homogeneous. If we look at the fabric of the material, if we look at these forced chains, you could say that the typical network mesh size, if you like, the typical size of these loops here, is of the order of 5 to 10 times the particle size. So you could say, well, perhaps then the network is going to be characterized by that sort of dimension, and so that a continuum could be described as being one which has scales of about, well, perhaps 10 to 100 times that, so 500 to 1,000 times D50 here. So if you stand back and look at a network of that size, then you'd see essentially homogeneous heterogeneity appearing in the material, if you can imagine this concept. But it's just defining another scale which is considerably bigger than the size of individual particles. So the question was, how large should the sample be to appear homogeneous? And the answer is that it's much larger than you thought. And this has implications for the size of the homogeneously heterogeneous test specimen that you might choose to use. There's also this clear result we find that these heterogeneities, these changes in the non-uniform structure of the deformations appear very early in a test, instead of not late on. So those are the conclusions for that particular section. Now the next one is then going to be deficiencies of the sample, or the test. And we'll look at two apparatus, the triaxial apparatus, which has been mentioned already this morning, and the simple shear apparatus. Well, we know that if you have triaxial samples, then sometimes you may find that the imposed stress state is actually axisymmetric. We have a cell pressure we're applying around the sides of the sample, but there's no particular guarantee usually that the soil specimen has a vertical axis of symmetry in terms of its anisotropy and its fabric. So it's being compressed between rigid platens, but there's no particular reason why that should result in a axisymmetric stress state within the sample. So it may be, if you're lucky, that actually there is a resulting axisymmetric stress state, but it's only going to be by chance rather than by routine. So the deformations are not constrained to follow any particular symmetry, but our measurements always assume that, because all we do is measure the external axial strain and volumetric strain, and we assume that axial symmetry without any challenge. So it's very tempting to assume that things that you don't choose to observe don't even exist. You imagine this is a sample taken out of the ground with a natural anisotropy which is not clearly vertically oriented. We try to subject it to triaxial compression testing with either a rough ends or with smooth ends, and the sample will do what it wants to do, but it won't behave uniformly under that imposed constraint. Well, there's wonderful work been done at Grenoble by Jacques Deroux and more recently by Eddie Ando, looking at using tomographic techniques, using X-rays, for example, to detect variations in soil density, from which we can produce really quite elegant and intricate mechanisms of internal deformation. These are ones which show the volumetric strains that he picked up in the 90s. And these are sections you can see through a triaxial sample, and if you try to put them together, you get these really rather fancy, amazing mechanisms of volumetric strains occurring within a triaxial sample. So this is a sample which we think is behaving in axial symmetry, and here we have these mechanisms which are clearly not axisymmetric mechanisms at all. It's behaving in a totally different way, a free way, if you like. And these are taken from X-rays at various stages of the testing. And in fact, if you look at the volume changes within the shear bands, then you find you get a consistent critical state condition, whereas away from those bands, you get a much more delayed response. So the tracking density changes shows that the critical state is reached within the dilation bands, but not globally within the sample. This is more recent ones, more recent imaging done by Eddie Ando and Jacques Deroux, which are fantastic pictures showing variations in distortional strains within the sample. So these are totally not axisymmetric pictures. They're mechanisms of deformations which are beautiful and elegant, but are showing something quite different from an axisymmetric response in our traxial sample. And we await more talk about these pictures from the Grenoble people. So the implications that we see from these pictures is that we've got individual mechanisms which are far from axisymmetric. They reflect the response of the sample to the imposed stress and the boundary displacement constraints, but the response which is very specific to the triaxial apparatus and nothing to do with what happens in the ground. And again, once again, we see that precursors of such mechanisms are very small deformations. So even from early stage of the testing, we're getting these deformations occurring. Now, I did my research at Cambridge. I started my PhD research just after Roscoe had been killed, but he had an obsession throughout his research career of simple shear testing. Perhaps he's right, I don't know, but he was very keen on that device. But the simple shear device is well known to be flawed because there is an absence of boundary shear stresses on the head of the sample here. So without the shear stresses there, you need to do something about measuring the distribution of normal stress, which itself is variable, as in the second picture, across the sample. And one way to cope with that is to surround the sample with load cells, so stress measuring devices, as in this bottom picture here, which essentially is an apparatus used by Stroud, whose name was mentioned this morning, for looking at the behavior of sand under simple shear. So that's the way of looking at the stresses. And with X-rays or radiography, you can look into the sample and see the density variations and try to see what is the effect of the sample size on the density variations, patterns of those that occur within the sample. And the question we can ask ourselves here is, how high should the sample be? What should its dimensions be? Should it be just high enough to constrain a single shear band? That feels too constrained, but it's one possibility. And essentially that's the one that Stroud adopted, so you had a 20 millimeter high sample for 1 millimeter size sand. But alternatively, you might say, well, let's make the sample high enough to allow free development of internal shear bands. This is a picture from Dicky Bassett's work. But then you start seeing elaborate internal patterns which are strongly influenced by the corners of the apparatus. So these variations of density here are essentially really rather curious effects produced by the corners of the device. So the ideal sample height perhaps depends on the size of the material being tested. I mentioned that when we're looking at the behavior of these columns of particles heavily loaded, that they are very sensitive to rotation of axes. And as a corollary of that, one might say, well, one should be looking at laboratory tests which try to themselves look at the effect of rotation of axes. But you'll see that the possibilities that we have are limited and all rather flawed in their different ways. Obviously, the direct shear box is producing a very localized behavior. Simple shear we've just seen has these problems with the shear just on the ends. Directional shear is the essentially Grenoble device, very complicated. And the hollow cylinder, well, the hollow cylinder has variations with radius of every stress and strain component, and it's difficult to actually sort of assess the uniformity of results from such a device. So the conclusions now we have are these, that the samples, most testing seems to show local features of response which don't conform with the overall boundary responses, and they appear at small deformations. Heterogeneity seems to be the norm even within geometrically desirable specimens. Rotation of principal axis is important, but the testing possibilities are flawed. Is there an ideal single element soil test? I think probably not, actually, but that's the participant's point. The next one then is an easy one to deal with, which is the deficiencies of the model. We've looked at the problems with the sample and with the apparatus, but what about the model? Here we could say that Moore Coulomb provides an easy target, because typically we have to do something like this. We have a result of a laboratory test shown as deviated stress against shear strain. So clearly a non-linear response there. And the volumetric response also shows nonlinearity. So we have nonlinear responses in terms of stress-strain behavior and in terms of volumetric behavior, and yet we're trying to fit those with a so-called Moore-Coulomb model, in which we've got to choose stiffness, strength, and dilatancy to match these data. We can't do it. We're trying to fit two lines to a curve. So it's an interesting exercise, and if you have a class of 2,000 people as in here, everybody would produce a different answer, and each answer would require its own narrative to describe why it is you produce that particular set of parameters. It's obviously a hopeless model because we're trying to fit a curve with two straight lines. And if you're faced with a hopelessness like that, the best thing you can do is to change your model in some way to improve the match with the observation. Let's just quickly look at the problems that we have with this material. There are three problems, basically. One is that the incremental stiffness is either elastic, so it's high, or zero for failure. The second one is that we have indefinite dilation or compression going on at failure. And the third one is that strength is chosen as a soil constant. But in fact, we can deal with all three of these errors, defects, by making some simple changes to this Moore-Coulomb model. The first thing is this one here. Rather than using a straightforward elastic analysis, we can say that the stiffness varies steadily with strain, and as the strain increases, so the stiffness reduces towards zero. So that we introduce a monotonic increase in strength, a reduction in stiffness with strain. That seems straightforward enough. The second one is to introduce some dilatancy effect, which is going to say that the volumetric straining varies with density and with stress state during the test. And we can see some evidence for that from classic work from Taylor, where we have a shear box test, always good value. So mobilized friction against deformation here, volumetric change against deformation there. And if you look at the slope of the volumetric change graph and plot that against the mobilized friction, then you see something which is essentially a linear relationship or a sublinear relationship between the two quantities. So there's a link between the dilatancy, the volume change, and the mobilized friction of the material. So that's very easy to do, introducing that dilatancy law. And the third thing to do is say something about strength. These are tests on steel balls done by Peter Roth back in the 50s, and he was looking at the effect of having different densities, different stress levels, on the ultimate state that you have for this material. So the left-hand diagram shows the void ratio against deformation in the shear box. The right-hand diagram shows the end states of these various tests. So here's an end state there. All these different initial states produce the same volumetric packing at the end of the test. So the end points fit onto a clear line in terms of the stresses and the volumetric change, a clear critical state line linking these final states of these tests with different starting points. So we introduce this idea about asymptotic critical state strength, and such ultimate states define a critical state line. Once you've done that, then you can say that you can define a quantity we call state parameter, which is an indication of how far the soil is from its eventual state. And we can then find that actually all aspects of stiffness and strength of soils are dependent on this value of state parameter. And the message is this one, that soils know how far they have to go. So they know that this is the distance they have to go to get to failure. They have a feeling for that. And this idea about state parameter generalizes the ideas of loose and dense definitions. Anything above the critical state line is loose, anything below it is dense. So it's a combination of stress level and density. So what is peak strength? It's not a constant, it's actually a dependent quantity, because it depends on the current strength, depending on the current state parameter. So depending on where we are just now, we'll have different values of the current strength. So we have an idea about linking the peak strength, the current strength, to the current value of state parameter. So that we have a complete model. We call it Severn Trent sand. It gives us monotonic shuffle towards the current strength. The current strength depends on the current density. Shearing leads to a change in density through dilatancy, and the change in density leads to a change in strength. So it goes around in a loop here. And so that the predicted peak strength is actually an emergent property of the model. So we've got those various stages that we've just described there. And what we see is that miraculously, although we had very simple linear or monotonic relationships, Once you put them together, you find you get a model which actually shows peaks and softening, dilation or compression, depending on the value of the state parameter which we're testing the material. So now we've got a model which actually is able to reproduce the observed response for the real soils without the need for arbitrariness or for a narrative. It's just a molecular model with extra features added to it. Why do we carry on using the molecular model, I wonder? There are several other candidates which are very similar to this one, which will do the same thing in terms of the ability to describe the variation of response with stress level and density. So, conclusions now. So all testing is conducted in the context of a particular model, whether you think about it or not. The interface between modeling and testing is challenged by deficiencies of the testing, but also by deficiencies of the model. Internal heterogeneities are typically observed from an early stage. Single-element tests are not single-element tests, they are systems, and there's a challenge of deconvolution to try and work out what's happening from the observed external response. The structure of heterogeneities suggests that the unit cell has a scale much bigger than D50, which has implications then for the dimensions of test specimens or physical models on the material. Where you have a model and observation which clearly totally mutually inconsistent, like the Coulomb case, clearly an improvement of the model is required to improve the response. It is tempting to assume that things you choose not to observe do not exist. It's very simple to say we have a triaxial sample being observed and we measure the volumetric strain and axial strain, but there's all sorts of things happening inside the sample which you cannot see from the normal outside. There's probably no perfect test, but what we do need is more elaborate monitoring of the tests we do in order to reveal the actual response that's happening inside the soil. So that's the end of my talk, but just to sort of note here the tensions that are imposed on the modeler, the constitutive modeler, who is pulled by the fisherman trying to get physical realism, the kite flyers looking for mathematical elegance, and the tug-of-war thugs looking at numerical implementation. But these are all tensions in different directions, putting them in the modeling challenge. So I thank a whole range of people for their assistance at various stages in this lecture preparation. And I end with that picture again for you to spot your favourite friends from 50 years ago. Thank you very much.